Unlike London dispersion forces, dipole-dipole forces exist only between molecules with permanent dipoles, and therefore stronger than LDFs. Dipole-dipole forces are attractions between opposite poles of polar molecules. The more polar the molecule, the greater the charges, which results in stronger Coulombic attractions. On the left, between HCl molecules, the dipole-dipole force exists, but the melting point is minus 85 degrees Celsius, because the electronegativity difference between hydrogen and chlorine is 0.9. Where if you take hydrofluoric acid, HF, and the attractions between them, the difference in electronegativity is 1.9, meaning that's a much stronger poles and stronger dipole-dipole forces. The result is the melting point is 19 degrees Celsius. So at room temperature, hydrofluoric acid is a liquid, but it has just turned liquid, and if it gets much colder, can easily freeze and turn into a solid. Hydrogen bonds are a special type of dipole-dipole force that is generated between the highly electropositive H on a molecule and a highly electronegative atom on a neighboring molecule. Only fluorine, oxygen, and nitrogen along the right end of the second period of the periodic table are electronegative enough to generate the high positive charge on hydrogen necessary to create a hydrogen bond with a neighboring fluorine, oxygen, or nitrogen. Remember, that's very important. Let me emphasize that. Hydrogen bonding can only occur between fluorine, oxygen, and nitrogen. If there is no fluorine, oxygen, or nitrogen in the bond, it's got to be fluorine, oxygen, or nitrogen. Bond with hydrogen. If you do not have a hydrogen bond with one of the three elements, it is not a hydrogen bond. Hydrogen bonds play an important role in polymers, both synthetic, plastics, and natural, proteins. Hydrogen bonding stabilizes the secondary structure of proteins with a strong hydrogen-oxygen bond. The impact of hydrogen bonding. Hydrogen bonds create unexpectedly high melting and boiling points. And here you can see a list with hydrogen when it bonds with tellurium, certainly not a hydrogen bond, but it will be a strong LDF and have a boiling point relatively high, minus 2 degrees. When hydrogen bonds with selenium or sulfur, the strength of the LDF decreases, as does the boiling point. But all of a sudden, pop oxygen, which is in the same group as tellurium, selenium, and sulfur, bond with oxygen, and all of a sudden the hydrogen bonding makes the LDFs slow, but because there's so few electrons, but the hydrogen bonds are very strong, making it very hard much harder to break the forces, and water boils at 100 degrees Celsius because of hydrogen bonding.